and Architecture course. Take a moment, please, and think about these questions. When we talk about soil, what exactly are we talking about? Why is it important for a civil engineer to know the characteristics and properties of the soil when designing a structure and developing a site plan? In this lesson, the first of two about soils, we will be discussing the types of materials generally labeled as soil. We will also be describing characteristics and properties of soil components so that you are more aware of why this is so important to the concept of designing structures. The second lesson, soil testing, will lead you through the steps and procedures for testing a soil sample. Soil is formed from the effects of nature's forces on rocks and the remnants of living organisms that died over the many years that the earth has been around. Soils are comprised of a unique combination of gravel, sand, silt, and clay, each of which contributes to the engineering characteristics of the material. There is no construction material that has both the physical and engineering properties which are more variable than soil. Therefore, it is highly desirable to have some information regarding both the surface and subsurface conditions. Soil testing allows the engineer to classify the soil and to determine how the soil will behave as a construction material. Soil classifications determine the various physical properties of the soil and provides a correlation to the engineering properties. The soils underneath a building or commercial structure will influence the type and size of the structure foundation. Soil conditions can also affect the construction costs, especially if it is determined that additional materials or reinforcements are needed to ensure the integrity of the structure. Testing the soil informs the engineer about the bearing capacity of the soil. This is the soil's ability to carry the load without any failure within the soil. It can also be referred to as the stability of the soil. The load-carrying capacity of the soil can vary with the strength of the soils and the method and magnitude in which the loads are applied. The amount and rate of settlement for the foundation can be estimated for a certain known soil type. The building can then be designed to accommodate a certain amount of settlement. It is important for an engineer to understand the drainage characteristics of the soil. This aids in not only planning a structurally sound foundation, but also helps determine the site work which is needed for any particular project. In order for the engineer to determine the best design for a construction project and to develop a site plan, he or she needs to have several pieces of information. Engineers need to know the function of the structure, whether it is to be used for educational, small commercial, or heavy industrial purposes. Each building type will have different building loads due to the building materials selected and the live loads imposed upon the structure. Engineers need a contour map or site profile and a geological survey map for the area. In addition, engineers need soil property information which can only be obtained during testing. This information may be relatively easy to obtain if one was building a 1- or 2-story building, since only 3 or 4 shallow soil samples might be needed. As the height of the building increases and the building loads increase, the amount of soil sampling information and the sampling number also needs to increase. When taking soil samples, the location and the depth of the soil sample should be representative of the soils at the site and the type of structure being built. Most samples are taken 1 to 2 feet below the surface. Some construction projects demand the need for borings, especially if the foundation of the structure needs to support a large load. Keep in mind that the soils throughout the site may not be uniform. When this happens, the engineer must be able to determine if these samples are representative of the site or if additional sample tests are required. The Unified Soils Classification System is a visual, rapid method for identifying and grouping soils. It was first developed by Casagrande for military construction of airfields. This system characterizes the soil as either a coarse-grained soil, a fine-grained soil, or a highly organic soil. The coarse-grained soils are described by grain size, while fine-grained soils are described on the basis of their plasticity. By grain size, while fine-grained soils are described on the basis of their plasticity. The USCS uses a chart to help characterize the soil. This chart should be familiar to you. You saw it at least once during your summer training experience. It is part of the curriculum, Activity 5.1, Soil Testing. If you'd like, take a moment at this time to stop the lesson and review that activity. In order to determine grain size, soil sample particles are sorted by size. This is accomplished by shaking the particles through a series of sieves. Gravels, the particles of largest diameter, range from approximately 3 inches down to the size of a pea. Sand, the finest of grains, start just below this size and decrease until the individual grains are about 0.07 millimeter in size, about the size of a number 200 sieve. Silt and clay particles, those which pass through the number 200 sieve, are indistinguishable as individual particles. In fact, they cannot be seen by the naked eye when viewed at a distance of 8 inches. Sometimes it is rather hard for students to get a handle on exactly how big the particles we are talking about actually are. We have provided this chart to help both you and your students understand this concept. We invite you to pause the lesson momentarily and obtain a copy of this chart to share with your students. As you can see by looking at the chart, there are many types of soils. These particles range in size from boulders, which are over 12 inches in diameter, to silt and clay particles, which are very, very small. Gravels are separated into either coarse gravel or fine gravel, with a 3/4 inch sieve as the dividing line. Sands are classified as being coarse, medium, or fine. If the particles pass through a number 4 sieve, but get caught before the number 10, they are classified as coarse sand. If particles pass through the number 10, but stop before the number 40, they are considered medium. Between a number 40 and a number 200, they are thought of as being fine. Another idea which might help students understand the size concept is to have samples in your classroom. As you can see, coarse gravel ranges in size from 3 inches to 3/4 of an inch, comparable in size to a plum or a lemon. Fine gravel, on the other hand, would be comparable to a grape or pea in size. Sand can be demonstrated in the same way. Students will be able to observe that coarse sand is similar in size to rock salt, while medium sand is equivalent in size to sugar. Once soil particles have been separated into their various size groupings, they can then be described by their gradation characteristics. A well-graded soil is defined as having a good representation of all particle sizes from the largest to the smallest. A poorly graded soil is divided into 2 groups, uniformly graded and gap graded. A uniformly graded soil is one in which the majority of particles are the same size. A gap graded soil contains both large and small particles, but the gradation continuity is broken by the absence of some particle types. A gravel or sand soil type can be further classified as clean versus dirty depending on the percentage of fines within the soil sample. If a sample is identified as clean, it contains little or no fines. generally less than 5%. A soil which is identified as dirty if it contains more than 12% fines. Remember that fines are those particles which pass through a number 200 sieve and can be made up of both clay, a non-organic material, and silt, an organic material. In addition to the sieve analysis, the following soil tests will further define fine-grained soil as to the amount of clay or silt they contain. These tests are the dry strength test, which determines the soil particles' crushing characteristics, the dilatancy test, which determines the soil's reaction to shaking, and the toughness test, which determines what kind of consistency exists near the plastic limit. When examining samples for grain sizes, the shape of the visible particles can be determined. Sharp edges and flat surfaces indicate an angular shape. Smooth, curved surfaces indicate a rounded shape. Particles may not be completely angular or completely rounded. These particles are called subangular or sub-rounded, depending on which shape predominates. Platy is the name given to these particles which have one dimension relatively small compared to the other two. Clays generally fall into this category. Color is also important in distinguishing between soil types. Color may vary with the moisture content and sometimes indicates the presence of certain chemicals or impurities. In general, colors become darker as the moisture content increases and lighter as the soil dries. Some fine-grained soil with dark, drab shades of brown or gray, including almost black, contain organic colloidal material. In contrast, clean, bright shades of gray, olive green, brown, red, yellow, and white are associated with inorganic soils. Gray-blue or gray and yellow mottled colors frequently result from poor drainage. Red, yellow, and yellowish-brown colors result from the presence of iron oxides. White to pink may indicate considerable silica, calcium carbonate, or aluminum compounds. Another characteristic of fine-grained soils is its plasticity. This refers to the varying water content found in the soil. This system is sometimes referred to as the Attenberg limits, named after the Swedish scientist who developed this test. The plastic limit refers to the lowest moisture content at which soils can be rolled into a 1/8 inch diameter thread without breaking. The liquid limit is the minimum moisture content at which soil will flow when a small shear or cutting force is applied. These mean little unless they are indexed to other significant properties of the soil. Once a soil has been classified, it can then be grouped according to soil type, gradation, and liquid limit. Each is assigned to a unique letter which is then used in combination to form the different soil groups. Please look at the last column, the liquid limit. This refers to the moisture content at which soil changes from a liquid state to a plastic state. Along with the plastic limit talked about earlier, it provides yet another means of soil classification. This brings us to the end